In this video, we will apply the rational root theorem. It says to determine the number of real zeros that each polynomial function may have, list the potential rational zeros of each polynomial function. Now, it does tell me do not attempt to find the zeros, but I'll show you a little bit of what that process would look like. F of x equals 3x to the fourth minus 3x to the third plus x to the second minus x plus 1. Determining the number of real zeros that each polynomial function may have, the function may have up to 4 real zeros. The rational root theorem states that if p of x is a polynomial with integer coefficients like this one, and p over q is a zero of that polynomial function, then p is a factor of the constant term and q is a factor of the leading coefficient. So we are interested in this constant term. And the factors of positive 1 are 1 and negative 1. Those are the only two numbers that divide evenly into the constant term. Now we'll look at the leading coefficient. The factors of q are going to be 3, negative 3, 1, or negative 1. The rational root theorem says the possible roots of this function are going to be p over q. And what we get is positive plus or minus 1 or plus or minus 1/3. So there are 4 possible roots here that are real solutions. 1, negative 1, 1/3, and negative 1/3. Now, truly, I could stop there, but I did want to show you what this would look like if I took the polynomial function that was given and I assumed, and I wanted to test, is negative 1 a real zero of this function? If it is, then when I divide by x plus 1, I'd get a remainder of 0. Now, I'm not going to talk through this whole division process because we've done that in an earlier video, but I will just go through the division here for you so that you can see what happens and what would the remainder be if I divide by x plus 1. Remember, if I get a remainder of 0, that means that x plus 1 is a factor, and in fact, negative 1 would be a root. So we're looking for a remainder of 0. But we don't get it. So by the remainder theorem, since the remainder is not equal to 0, we know that x plus 1 is not a factor. Therefore, negative 1 is not a root or a 0 of this function. It's not a real solution of that function. So I've narrowed out negative 1. What if I wanted to try the same division process, but using testing the solution of positive 1? So here I'll divide by x minus 1 and see if I get a remainder of 0. So you can see that this does require quite a lot of work to do all this by long division, which is why we will talk about synthetic division in another video. It's a shorthand division process because this is a lot of work. After going through this whole thing, I get a remainder that's close to 0, but it's not 0. So that tells me that x minus 1 is not a factor. Therefore, 1 is not a root, a real 0 of this polynomial function. So now I've narrowed out my 4 possible rational roots. I could go through the process for 1/3 and then negative 1/3, but I think at this point I don't necessarily want to deal with fractions. So let me just type this into Desmos and see what this curve looks like when I graph 3x to the fourth minus 3x cubed plus x squared minus x plus 1. Well, what's interesting about this curve is there are no real solutions. So I'm glad I didn't take the time testing out x plus a third or x minus a third.